Yeah, I see the presentation. Looking good.
Okay, good. So my name is Vlad, and as you heard, I'm gonna show how you can get the length of the list or any type of iterable, which in very hard way. So before, let me see, hold on, let me get controls. Okay, so this is the easiest way to do it in Python. So if you want to get the length of anything that has a length, you just use the length function. So if that length function didn't exist, we can do it a little harder way. You can just wrap it around for loop generator, whatever iterative construct, like add as many times as elements, get the length. So if we did not have any of this construct, so we can resort to recursion and just write something like that, which is slightly harder. But so I used to think that I know what the recursion is and what define is in like sort of greater computer science philosophical things. But what if you have a language as you on Mars and like your computer breaks and you cannot define anything? Can you still get the length of like an iterable without any of this? So let's try. So yeah, this is the first time I'm doing live coding on the large presentation. So hope it goes well. So this is the development environment. So I usually do test-driven development, means like I define the test first. And actually, let me do one thing first, so you can see better. Is it better? Okay, accommodate for people and sometimes. So this is the development environment. So you in Testdriven driver, you define the test first, and you run it, and then you write the code that will make the test pass, right? So I have two tests here, as you can see. The first one is just test that standard recursive implementation, and I'm going to come up with the one that's that does not use define. So first thing I'm going to do, like, because in the test-driven development, you'll see like we get a failure, what's failing, right? It says we cannot import length tool. So we try to define it like this, and still an error because integers are not callable, obviously. So to speed up this talk, I made two little live templates for the PyCharm. Is the Parentify and Lampify. So I'm just going to explain as we go. First, we see what the Lampify does. It just surrounds the selected code that puts it on a separate line, and it surrounds it with the lambda, and it puts the argument at things. So it's, if you guys know JavaScript, that's what if is for. So this doesn't compile, obviously, because this X is not defined, so I'll just delete it. Okay, so we run the test, and we actually get the passing case for the first things when the list is empty. And if you don't know, if you're not familiar with PyTest, what I'm doing here, basically getting the length of the list of first the empty list, then list of length of 1 and list of length of 2. Like this is what the number is, 3. So we get the passing case for the empty list, but it doesn't work for the rest, obviously, right? And it's even worse. The function completes, but it gives a wrong result, which is the worst thing you can possibly do. It's like you run the program and it says like everything great, and but the result is not correct. So let's take care of that. So we see if I access false, which means it's the empty list, then we return 0. Otherwise, so we can't really do anything yet. So they define the little function here is crash. And I'll try to mimic what we're doing on the top here, and then crash, but I will add one to it. So we're still failing, but at least now we throw in exceptions. Right? So, and here we come. I have another little handy thing, template defined. It's called Parentify. All it does is just surrounds with the little, it puts on a line that surrounds with the parents. And so far, like that's the only things we're going to use, because I'm going to show like that we're not creating any new code. We're going to just use the PyCharm's refactoring things in this template. So that's the only tools we got so far. So actually, I'll just rename it to L to make it look like the tab function, and see what we can do about this crash. So it's like not really a good thing to do. So one thing I can do, because we cannot call it recursively anything, because if you're not familiar with lambdas are like the Python functions, but they don't have a name. So we cannot actually call ourselves again because there is nothing to call. It has no name. But what I can do, I can just paste it in here, and it's incorrect syntax because it needs the argument. So I'll just give it a rest of x, and hey, here we go. We can do it for the list of length and 1 and 2. So what I can do next, I can just cut and paste this thing again, and I paste it in here again. Paste it more. All right, so we can do it for case of 3, and you can see you can do this stuff indefinitely, but this is not very good computer program because you have to have as large program as the large list you can process. So if you can, for example, try to do the length 4, you're still crashing. So as you've seen, we only have like a few things we can do so far, right? So let's just try to Lampify again, because I just don't like this code that's crashing in the middle. And now we got an argument x, then I'll just put the crash together. All right, so we still run, but then we didn't get that much. But now what I can do, I can just get this lambda in here. And we have no x, so I'll just crash here. And here now we can actually do the 4 cases. So, but we're still failing on the 4 because we get exceptions. We cannot get the length of 4. So as you guess, we only have 2 tools. So what we can do again, we can just Lampify. And we don't have an x basically, so I'll just delete it. Yeah, so I guess we can also cut and paste and delete. That's like the only thing we can do. Now we get an error because this x returns the lambda anymore. It's not really a function, it's lambda a little bit different beast, but you can think of them as functions. So it needs an argument because you cannot add function to an integer. So we need to pass something. We only have 2 things. I mean, we can pass an integer, we can pass an L, or we can also pass an X. And now we still crashing here because we have to call it. And now we have no crash anymore, but we have exactly the same problem like we had above. So I'll just replace it with X. And hey, we're going with here. So what if we replace it by 6? Let's go. So what if we replace it by 66? It still works. We replace by 166. Okay, so now we got the working program, but the problem is it's extremely ugly, like because we have all this stuff. Like, so let's see if we can simplify. So what if I don't pass the rest of the list and I don't need to add 1? Okay, it still works. Okay, I didn't cut and paste too much. Oh, and I guess we can reformat the code. So now this if statement doesn't really do anything, so I can just delete it. And let me reduce because we see that works with the rest of this. We'll just speed things up because we have a limit time. So now this lambda doesn't really do anything, so we can just delete the lambda and the call. We're still working, right? So again, we can reformat. We can drop this little thing and over. Okay, we're still working, and then we can also remove redundant times. Now this if statement is useless, so we just delete it. Okay, we still work. So now we delete that. So we just repeat. So now I'm just not going to talk because we're going to do exactly the same thing we almost done there, right? And we get to this +1. Okay, so this if statement is useless. And that's a good thing about TDD because you can go refactoring code and you make sure, like, you know, you haven't broken anything. So we have too many parentheses here. We just remove it, delete it, and we got the last lambda, and we delete it as well. Okay. Okay, I need to do the lambda. And remove the parentheses. So we got something a little better. And if you look on the top of the recursive definition, we got almost something like what the top is. So I just call it the violence. So we almost have it, but except actually it's not a violence. I call it because what this function does, this lambda does on top, it creates the length, this thing. So I just call it the make length. Right. So it almost okay, but it doesn't exactly look, we have this ugliness here. So as seen, like we only have a few tools in our toolbox. So what we can do, we can just actually not this expression. Right here, what we can do with it, we can first Parentify, and then we can Lampify. Okay, and then we get this stuff, put it here. So at least we got it out, and now length looks exactly the same. But then, oops, something happened here. So problem is this never returns because it's just gonna call itself all the time. So what we can do, we can almost Lampify, but that my template's not that good. We can round it with lambda. Okay, now it works, and you can see we haven't broken it, increased to 26. So we got it there. Okay, and then because it's not make length, we can just call it an F. Great. So then we format, and then let me just arrange things a little bit. And look, so that's one on the top and the one right here, it's actually exactly the same. I'll just call it violent. So we can create it. And let's delete this set of files. And we actually don't. So we got exactly the same thing like on the top. The only problem here is this stuff, like our function we basically accomplished, but it's in the middle of this strange construct. So what we can do with it, I guess, like the drill, what the things we can do, so we can just Lampify them. And we got too many x's going, so I will just call this right. Oh, okay, yeah, so this one, so just name it to y. Okay, and now we can get this expression. This one. I want this expression, and I just replace it by x, and x goes right here. And we haven't broken anything. So the last thing I'm going to do, I'm just going to extract it. So PyCharm things, I'm going to extract this construct out there. And a little bit better. Okay. And here we go. So we actually have the function, we have one extra. We have one extra. This one, I think we can do it. Here we go. So we actually now we can define things without having defined and using this strange construct. And what's interesting about that thing, we can also define anything that's computable. So we can have a function, for example, we want to come up with the sum of numbers from 1, 2, 3, 4, 5, right? So we give a number n. So the sum is 0 if n is less than 1, but if it's more than 1, it's wait, hold on, we need one more. Sorry, no. So because we actually need to create outers, so we call it my sum. And then this is the definition of the function, which is 0 for the if 1. And also just n plus my sum and I have the test for it that tries to put the numbers from 0 to 100. And that is like so. And actually, anything that's computable, it's computable, but this thing that's called m. So let's see what that strange m thing is like. So if you're like just look at it closely, it's just 3 lambdas. It's actually, I think this lambda is not necessary, I believe. Okay, I'll just leave it like that. I think we didn't refactor correctly. It should be 3, but it's the lambdas plus the thing. So if we heard about this company, like it's a like Bay Area company that's like venture capitalist company, and they create things. But if you see the Wikipedia article, so it's actually, they didn't come up with the name. If you see the little thing on the top, they refer to something, hey, you probably, so most people who search for y-combinator, they search for the company, but here is this little thing on the Wikipedia. And if you look at it, it's a little bit different syntax, but this is 3 lambdas and bunch of this FNXs. Right? And that is a fundamental thing in the computer science, because using that thing, you can, that's the only thing you need to compute anything. So if you have some kind of machine that implements the y-combinator, you can compute anything. It's like equivalent to the Turing machine, except it's more abstract. And actually, it was created by Haskell Curry, and Alan Turing was actually his student. So that's the thing is. So going back to the things. So where I got it, so this is more information about it. So the one I actually, when I start questioning, so there is this book called Little Skimmer. It's great, like if you want to learn anything about computing and like in very like what the computing actually is in computer science way. And it's kind of bad because you start reading it and it thinks it's elementary, but when you goes through the second half of it, because I have like a lot of experience being software engineer, when I got to like towards the end of things, I kind of like start questioning my sanity, like see what I don't understand what computing is like. But then when you go through this exercise, you kind of gain your sanity back. So Little Skimmer, this is also like a pretty good book to, it kind of builds on, because actually I read this one first. Oh yeah, that one, exactly. But that one, it doesn't go into lambda calculus, it's more like hands-on, but it's actually, they're written by the same people, both of them. And Little Skimmer, it's written like as a dialogue. It's very like interesting. And if you don't, so the problem is with the list, but actually this whole thing, it's also a proof that you can, I know somebody said you can run Fortran in any language. This is a proof that you can write Lisp in any language. You don't actually need Lisp to write Lisp. You can just, and there is this book like from O'Reilly. It's actually, it's almost like Little Skimmer, but it's more mathematical, and it uses Ruby as an example. So if you, I'm not aware of the Python-based book, but if you hate Lisp, like you can use Ruby and it goes through that. And there is this person, Computerfile. He has a great talk, but he does it on the paper. Just and I just recommend if you bored, watch all his videos. So that's it. So any questions?
What are some of the advantages of doing it this way? The lambda
advantages? There is no advantages. Like you never use it in practice, like ever. But its advantages, it enhances your understanding of like what the computer science is, basically, because if you can write the recursive function without being able to call the function by name, right? Because if you can see it, because one thing we can do with this code actually, like we don't need any names. Like if I get this whole thing and paste it in here, and I don't, wait, I pasted it in the back in the same. Yeah, actually that was correct. Okay, I was confused a little bit. So if you,
so you only have to define one thing.
You don't need to define anything. So this is our test right here. Let me see, where is our test? This one right here, right? So we get rid of this import. We can just inline like when one has no initialization. I think it has to be before. So you have to paste them in here. So you can just inline it in here, and you inline the M.
And
So
so
we
it-
compute the length, we do not define anything. There is no single defined.
So you're using only the stack. You're not using, or not even the stack, whatever you call
There
it.
is no time. No, this is so fundamental. It goes beyond stacks. Like it's, there is nothing like basically. All you need to do is being able to create the lambda functions. Like if you can create lambda functions, that the only thing you need. And you
Yeah.
need numbers 1 and 0 and like,
So data just flows through this thing without
it flows.
being
It's very
stored
hard to
anywhere.
understand how it works unless you make it. And I don't know, we're not recording videos, right? On this one.
We are recording.
Oh, we are recording, yeah. So what I suggest, and when you go through a little scheme, like, because he actually says read this chapter one more time, because first time you read through that and he doesn't expect you to understand it. And then he said, read it one more time again. And I was reading it like 6 times. I could not understand it, but then I just did this whole thing in Python. And then I still don't understand how it works, but I know how to make one.
It's just, it'd be interesting to know what the properties of it are in terms of memory footprint and things like that.
They're terrible.
It
Oh,
actually depends.
It
Oh.
depends, yeah. It actually depends. So the only practical thing, so I used it 2 times ever, like, because if you go through a scheme, like this is the chapter before the last one, the last chapter you write your own Lisp, but they have like very limited version of Lisp, which is your, it has no define. But because you know this thing exists, then you can just use y-combinator and you can write any program in it. And after you write your own Lisp, you can actually get the copy of Lisp you written and then put it back in your Lisp you written, and you can stack it as many times as you want. And that's as a proof, because I didn't believe it, but after you did this exercise to implement Lisp, it's only 200 lines of code.
In Python, I'm pretty sure. Sorry, go ahead.
Yeah.
I have actually had a practical use for the y-combinator.
Uh-huh.
I wanted to have decorators in Kotlin. So Kotlin has higher order functions, but it doesn't have decorators, and I love decorators as they are in Python. The problem, a decorator is just a higher order function that is applied to another function. So, but if the function is recursive, then it's more than that, because the decorator is also applied to the recursive calls because of the renaming. So if I did that on a Kotlin function and I did it, applied it to a recursive function, then the decorator wouldn't be applied to the recursive calls. So the way to get around this was to use the y-combinator, because then there's no, well, I don't know, I don't remember exactly what I did, but I got around with it and I managed to make a decorator on a recursive function. The only problem is it's so ugly that it's unintuitive, but it works.
I don't think because the guy, little skimmer guy, says like nobody knows what the y-combinator actually does, because everybody knows how. I mean, you can learn how to make one within like a week, and you know what's it for. But how it works internally, it's really unintuitive, because it has things like that, right? It's so I mean, you can clean it up. So I think I removed too many things.
From a performance perspective, in Python, in C Python, I'm pretty sure it basically just makes a function that you would call it. It would be a stack. It would have a new function stack and everything on it, or a call stack rather. But that's language specific, and different languages may implement that differently. And they could actually unwrap recursive calls into non-recursive calls. There's potential magic.
Right. And I know some like Ruby, so I was surprised somebody used it. I know there is a Ruby library that uses that for some strange reason. And if you read the standard compiler book, the one with the dragon, they actually have the useful y-combinator, but nobody really gets that far, and people write compilers without actually doing that. Because there's actually very few languages use the formal definition of language, and like they kind of just write ad hoc parsers. And